record on this computer. Okay, so what we have is three kinds of mixers. One was the Gilbert cell mixer, right? The which I had shown you. The other is a double balanced mixer. The performance a lot depends on the symmetry, or basically the choice of your center tap or your Balin implementation. Okay, the performance of harmonic wise, even harmonics are going to cancel out. That basically depends on the choice of their diodes and how well they are matched, and also the choice of the center tap on a Balin, or the way you implement the Balin, right? So basically, mixing, it's going to give the mixing, but the question is, are you going to get other harmonics? So even harmonics can be canceled out by a very good symmetry. That's all I'm trying to say. Over here, what I'm showing is what is called quadrature mixer. Okay, what we do in quadrature mixer is we use a hybrid. Now, usually this is used for down conversion, because in down conversion, let's say we do a 0 IF or let's say low IF. So this RF frequency is going to be same as the LO frequency. So if you remember in the morning, I showed you a slide where I said that, if it's a direct conversion, then RF and LO are the same, right? And then you directly get the baseband if you mix it. So in this case, what happens is the isolation between RF and LO is a problem. In a Gilbert cell, what do you have? In a Gilbert cell, you have two cells like this. Okay. So you have got two cells like this. Okay. And these are connected like this. And this basically is a translinear cell. And then you have two cells like this. Okay. And then there's a tail current which you draw from here. Right. So your Vx plus and Vx minus is over here. And then you have got Vy plus and Vy minus over here. Sorry, this is combined. Sorry, there's a mistake here. Okay, so what you have is you have your Vy minus over here, and this basically is shorted together like this. Okay, so now this, okay, this is cross. So basically this goes here and this goes here. Okay, so there is a resistor here, there is a resistor here. This is supply, this is supply. This is what a Gilbert cell looks like. Just 1 second. This is what a Gilbert cell looks like. Now, the problem is, let's say Vx and Vi, what is the isolation? The only isolation point over here is, there is no isolation as such. Okay, why? Because if you see between Vx and Vy, the only isolation path is over here, right? So here, what do? You can put resistances here, right? Here you can put resistances. Okay, so this causes the drop in the gain. Okay, so a drop in the drop in the gain is because of your source degeneration on these transistors. Okay, but then it offers a certain isolation between Vx and Vy. So it offers a certain isolation between Vx and Vy. That's the only option you have in a Gilbert cell for isolation. So if you are to use Gilbert cell for down conversion, your isolations will be of the order of 18 dB or 20 dB at the best, after putting resistors also. And in that whole process, you would have killed the gain of the Gilbert cell to almost 0 dB. Okay, so you can use a Gilbert cell for down conversion because it's the smallest one. Okay, so this is the smallest one you can have. But then you have to worry about the isolation between RF and LO. And in a direct conversion, RF and LO are the same frequency, right? So in a Gilbert cell, you are only left with putting these resistors in the source. Okay, so these resistors in the source, that's all you can put in here for isolation. Okay, so that's a big issue, okay, with the Gilbert cell. Now, coming to balanced diode also, it suffers from almost similar stuff. Now, the one which is really good in isolation is the one which uses a hybrid at the input. So we know that 1 and 4 port are isolated. So which causes the very good isolation between RF and LO. Now over here, what you do is you put a square device. So this is a square device, correct? Now let's say if I do a decoupling here, let's say, and some decoupling here and like this. So these are two devices which I have put here, right? Now what I'll do is at the output of this, I am going to put a stub, which is an open circuit stub. And here also I'll put an open circuited stub. Okay, what this stub does is at your RF frequency, okay, it is going to do a short. So if this is an open circuit and if this is lambda by 4, okay, so then over here this will look like a short. Right, so this short I show to the output. So that causes whatever you put in here is going to be reflected back into the device. So when it is reflected back into the device, it is going to square. Okay. Similarly, on this side also, it is going to square. And if you put a low pass filter over here, or rather if you match this to IF, so let's say if I match this to IF or low frequency, okay, then what's going to happen is all you get is a differential IF out. Okay, and these two devices acts as a squaring device. Okay, so the inputs are matched to RF while the output is matched to IF, and this causes the conversion. Okay, so this causes the conversion, and what you get at the output is a 180-degree out of phase. Now if you want to see the theory of this, you can find out. So this is called quadrature mixer. The quadrature mixer has a good advantage. The good advantage is RF LO isolation. And this is very helpful in reducing what you call DC wandering. Okay, so if you have a good isolation between LF and LO and RF, then the DC wandering problem is more or less, is gone. Okay, so that's the advantage of using a quadrature mixer. So usually when I do a very high frequency design, I would always do a quadrature mixer on the receiver side because it's a direct conversion and I want a good isolation between RF and LO. Okay, so let me look for a presentation where I can show you what's going on. Okay, quadrature mixer. Trainings. I don't know if I have a training which I did at Telecom Malaysia. It was a 60 gigahertz mixer. RFIC building blocks, key site. I wanted to show you quadrature mixer. Software, documentation. No, not documentation. PowerPoint presentation. No, it's not over here. 60 gigahertz presentation. Okay, so in that, I'll pull in the slide. If I get a gap in between, we'll have a break. I will do the mathematics for this quadrature mixer so that you will see the advantage of using a quadrature mixer. And the only drawback is it uses a large layout space. So in that case, I took the hybrid and I replaced it with a lambda equivalent. Or you can also do it this way, that you can meander the lines of the balun, and then you can get the on-chip balun, on-chip hybrid, on-chip hybrid, and you'll be able to do that. I want to show you that so that we just put it aside. Put it aside. How come? Maybe it is over here. Yeah, it should be in this. Just 1 second. Let it open. Okay, I want to show you a hybrid. based quadrature mixer, right? So yeah, so in the first lecture I was mentioning that in Genesis there is no PDK, but here I have made a PDK for Genesis where I have both bipolars as well as MOSFETs. So it's what I'm doing is, yeah, no, this is inductor layout. You can do the same workshop in any software. Okay, what's the advantage? Okay, so for example here you can see the chain, but then you will see all the things like budget analysis like this, like you will see the contribution of each component. This is what a Genesis does. I am looking for quadrature mixer. Okay, so that's a hybrid. Okay, so I'm just explaining what a hybrid is. Then where is it used? Okay, LNA, noise, voltage control oscillator, and so that's a VCO, and then the mixer. This is a Gilbert cell mixer. This is a quadrature mixer. Okay, so what is happening? So I'm just going to copy everything over here so that I can paste it in the new slide. Control C, and then I can share it with you. Okay, so I'll say quadrature mixer. Okay, and then I should also put the slide of Gilbert cell mixer, right? So that you have both the theory. Okay, so you have Gilbert cell mixer. Okay, so I'll copy the equations of Gilbert cell mixer here. So emitter, this is going to be source. Okay, so this is going to be using MOSFETs. So I'm going to copy this and I'm going to paste it in this. Okay. Okay, so I'll share this presentation so that, you know, later on you, at the end, you will have everything. So what is happening over here? Okay, can you see stuff right now? Wait a second. No. You guys can see my screen, right?
Yes, sir.
Okay. Okay. So now see what happens. I have RF going in. It will be 90 degree out of phase, so there is a minus 90. And then the contribution from here would be LO, and this will be minus 180. So I have the sum of the signal going to this transistor, and then I have got RF minus LO minus 90 over here, and RF minus 180 over here. So because this path is 90, 90, so 180. So RF goes through a 180 delay over here, and LO goes over a 90 delay over here. Similarly, over here, LO goes over a 180 delay over here and 90 delay over here, right? So now if you take these two signal, V out 1, V out 2, and do a square of it, and then after doing a square, okay, you are going to basically filter out, okay? So the DC would be gone because you would have a capacitor in here. No, you will not have a capacitor there. Okay, so you have to live with the DC because it's a direct couple. Then what you're going to have is, after simplification and after low pass filtering, you will be left with this RF minus LO. Okay, so then you will be left with two of this. One will be positive, other will be negative. So you will have a direct differential output. So you don't need a balun to go from single-ended to differential. So in this mixer, RF is single-ended, LO is single-ended, and the output is differential. Okay, you don't need a balun. It directly gives you a differential out. Okay, so that's your IF frequency. So this quadrature mixer is good for down conversion because there is a 1 and 4 port which are isolated, and this isolation is as good as 40 dB or so. So this is very good for your direct conversion receiver. Okay. So let's go back to putting this chain together. What has happened here? Nothing. Recording is going on. Fine. Okay. So now let's go back to the schematic. So we are going to put together a receive chain. So I will call this as RX chain. Okay. Okay. So first thing first, I'm going to put a mixer. Okay, because mixer is the bottleneck over here. So I will go to system algorithmic. So system amps and mixer. I'll put a mixer with allo, right? And this is going to be 50 ohm. And this is going to give you RF minus allo if you want, or I can give it standard. So it gives both sides. And then I would put a conversion gain of, let's say, it's going to be a conversion gain of 8 or 10, right? And then I'm going to put a return loss here in dB. So dB polar minus 10, and again in dB. So dB polar minus 10. Okay, so that's your return losses. And noise figure, I'm going to put 4 dB. Okay, SOI TOI. So now here, I want that the receiver should be able to take in, let's say, minus 10 in. And the conversion gain is 10. So it should be able to put out 0. That means that TOI, I'm going to put around 11. SOY, I'm going to put around 20. Okay, or rather, let's go 14 dB. So to be safe, and let's go this as 24 dB. Okay, so this is done, and then we will put a LO frequency here in gigahertz. Done. Apply. So our mixer is here, right? The impedance is not milliohm, it is ohm. Okay, conversion gain, input match, output match, noise figure, SOI, and TOI. So that's all the parameters are over here. Okay, now the next thing is I'm going to put here some kind of a LNA, right? So let's put a LNA here. Okay, so what is there in the LNA? You are going to have a certain gain. Let's put a gain of 10. Okay, and so if this is going to be compressing at 0 in, right? If it is compressing at 0 in, right, and its output is going to be 10 dBm, that's why this SOI and TOI. So let me put the TOI also. Hang on. Yeah, TOI is 14, right? So 14 means it's a 0 here. Okay, so this is 10, gain of 10. So this would be compressing out at minus 10. Okay. And 14, 0, compressing at 0, 0 out, and gain of 10. So minus 10 in. So this should compress as minus 10, right? So gain of 10. So this should be minus 20. Okay, so if it's minus 20, 1 dB compression is at minus 20. So dB polar minus 10 and dB polar minus 10. This is the return loss. And I am not going to play with this one. I have burnt my hands. Okay, this is okay, noise figure. Okay, well, now here you should know, if you are working with CMOS, you don't expect anything better than 3 dB. If you are working with let's say gallium arsenide Pmos, you can put there again 2 dB or 1.1 dB, 1.5 dB or 2 dB. Between 1 and 2 dB it will be. Okay, if you are working with your SIGE also, you are going to be in the range of 3 dB. So that's what I'm going to keep here. And next is TOI, SOI. So this should deliver at least minus 10. Okay, because this is compressing at 0, right? With a gain of 10. So this is minus 10. So this has a gain of 10, right? It has to deliver minus 10. So then this TOI would be of the order of 4, 5, or 6, right? 5. let's say this is going to be 15 or 14, whatever, right? Okay, TOI, SY, apply. Okay, so now we have a part which is going to compress at minus 19 or something, right? And it is going to deliver over here as, okay, so if it is going to deliver as a 0 dBm out, okay, so overall there is already a gain of 20 here. Okay, so I want to deliver a certain power for my what you call analog to digital converter, right? So this is beyond the detector. So I want to add here some more gain. Okay, so let's say, okay, so let's put a gain here. Now this is, there is no frequency dependence, so that's why you are able to do this. Okay, so let's put a gain of 20 dB here. So overall gain will be 50. Or if you want, you can put a variable gain also. So we'll put a variable gain also. Let's see, dB, and this will be minus 10. And this will be dB polar. It will be again minus 10. These are the return losses. And this I will not touch. And noise figure is as bad as 8 or something like that. And TOI, SOI. So this is 1. So let's say, okay, I'm at 0 here. 15 dB gain here on the variable stage. And then this one will be 15. And let's say 20 dB gain over here also. So 20 dB gain over here, 15 plus, okay, so 20 will be 35 or something like that. Okay, so 35 or something like that would be there. Okay, so then TOI would be 46 and SOI will be 55. Okay, TOI, SOI. Okay, and these are return losses, and say okay. So this is going to be your IF amplifier. And then I will put a variable stage here, which is going to be voltage of 1. Okay. And a DC voltage here, a DC voltage. Sources, frequency domain, and DC voltage here of 1 volts. That's fine. So 1 volts means it's a gain of 15. Okay. So now this stage is ready. Now, one more thing is there, filters, right? So here I'm doing a down conversion, right? So I will put here a filter, which will be the same filter as at the input of a transmitter, because I have come to IF frequency, right? So pick up your TX chain over here. Let's pick up this filter, and then this filter is a BPF. Let's pick up that also. Control C and Control V. Okay. So what do we have? We have a band pass filter, which is at your RF frequency. So this is at RF frequency, which is at 27.6. LO frequency is going to be your LO frequency is going to be your LO. Okay, so this is your LO frequency, and this will be around your IF frequency, which is around 600 megahertz. Okay, so this is around, corner is around 1 gigahertz, so that's fine. So we are done with most of the filtering here, right? And all we need to do is do a single tone, or a two-tone. If you want, you can do a two-tone, but let's do just a single tone, and then we'll do the budget analysis on this. So all you do is go to sources, frequency domain, sorry, P1 tone, and you are going to put here a RF frequency. So I will put RF FREQ. Sorry, that will be power, RF PWR. And then you have RF frequency. So this is your input. Okay, so I am putting RF frequency in at a power level of RF power, and this is going to be around 27.6 gigahertz, right? And then LO is around 27, so I have a variable for LO. So that LO is 27. Sorry, LO is 27. Okay, and then I would put here RF. Sorry, LO is 27, and then RF FREQ is going to be 27.6. Okay, so these are the two frequencies. What happened? Okay, LO is 27, RF is 27.6. So this 27.6 goes in, gets filtered with a BPF, put it into a LNA, okay, and then it goes to the mixer where it mixes with 27 and generates 600 megahertz. And that 600 megahertz goes through this filter with a corner of 1 gigahertz, is going into these two amplifiers, and then we are at the output. So at output, I'll put another terminal. Sources, S parameters, terminal. Okay, this is a 50 ohm termination. And then I'm going to put here the same stuff. Very quickly, I'll do that so that you don't get bored. This is I out. And then this is going to be, yeah, here it's going to be V out, right? Okay, fine. So we are all set with this. Now let's put a harmonic balance simulation on this, HB. Okay, and in this case, my frequencies are LO in gigahertz, and then RF FREQ in gigahertz, and that's it. So we have that. There's going to be mixing here, and we get to the output. So first thing I'm going to do is just a single point to see where my mix components are, right? So as we did with the transmitter, same we do with the receiver. We just find out the mix components, right? So I'm going to do it at a certain power. Okay, so LO power, sorry, you have to put in power also here. So RF power. Let's say I'm going to put here minus 20, which is 1 dB compression point. Okay, I'm putting minus 20, and I am going to do a run on this. Okay, what does it say? DC path corrected. So this is because of the filter. So don't worry about that. Now, what am I going to look at is the mix table. So when you look at the mix table, you have got 27.6 as one tone. Okay, so this is your input, RF input. Then this one is your LO input, 27. And then this one is your F2 minus F1, right? So that is going to be 600 megahertz, right? So this is the first one only. Okay, so once you have done that, now I can do a sweep, a power sweep, and then plot it. So before that, I'll just do a brief equation, measurement equation on HP. Okay, and very quickly I'll write this out. P out is equal to 0.5 times of real of V out into complex conjugate of I out dot I. Okay, so this is going to be your power equation, and then P out in dBm. Okay, so we are looking at only the first component. So P out at dBm, let's just do this, is going to be 10 log 10 of P out, okay, plus 30. Okay, so this is a P out in dBm, and the gain So P out in dBm, sorry. And gain in dB. Gain in dB. Okay, so gain in dB is going to be P out dBm1. P out dBm1 minus RF power. That's going to be your gain. And that's it. So this is going to be your overall gain. So let's simulate this. So is there any problem? No. So let me just write down the gain over here, or P out dBm. P out dBm. I'm going to look at the fundamental component, which is your component which you are interested in. So this is putting out 35.9, right? And let's look at the gain. That's a gain of 55. So the overall gain is going to be 10 plus 10 plus 10, 20, 20 plus 15. That is going to be 35. 35 plus 20 is 55. So the overall gain is 55. So the overall gain is 55, right? And let's look at the power, right? So with a gain of 55, I'm putting minus 20 in, and I'm getting 35 out. So basically, this is an uncompressed gain, most probably. So now what I'll do is I will do a sweep on the input power. So if I put a RF power sweep from, let's say, minus 80 to, let's say, minus 15, so that I cover the compression point, 0.1. That's okay. Say apply and say okay. So we are ready for that. I just hit this. Okay, I'm not going to look at this one. I'm just going to plot the gain. So that's the gain. And I'm going to plot the output power. So it will be the first index of this, as because 600 megahertz is the first index. So that's what it is. Okay. If I want, I can put this on right axis so that this will make sense. Okay, so this is your gain and the output power. Okay, so this power is at 600 because the index one is 600 megahertz, right? And you can also see the spectrum, P out dBm. And I want to, if I do this, you'll see everything, right? So what I'll do here is I will put a marker and I will find the index of this. So again, so n is equal to find index of the chain, which is RF power, comma, independent of M1. So that's your index. And at that index, I want to plot this. So if I go to the variable info and I look at P out dBm, so this is power sweep and this is your frequency. So for nth index, I want to see all the frequencies. And that's it. So just change the trace type to this one, and that's it. So we have over here, we have your required frequencies, and the other ones, these are not desired. So if I put a low pass filter, so basically if I was to see this node, so you say marker new, this one, so this is 600 megahertz, right? So I am putting in 66 and I'm getting it -8. Okay, so let's look at the next one, which will be over here. So let's say, what is this one? This one is 1.2 gigahertz. Remember that our filter has a corner around 1. Okay, and then you are going to see attenuation at 1.8 of 35. Okay, so that's that filter is doing. Okay, so you have a 35 dB isolation at that. You can also change this if you want. Only thing is going to change is the order of the filter. So this will go even further down, right? So basically it's this filtering which is deciding what you are doing beyond your conversion, right? So I'll put it back to 1.8. Okay, as far as the order of the filter, it will tell you the order for the BPF and order for the LPF is over here. Okay, so BPF has an order of 3, LPF has order of 5. Right now here BPF has only got a 35 dB isolation. Right, so image rejection will not be sufficient. So I can put a big number here, 65 or something. So now there will be a lot of image rejection. Okay, so it doesn't do much here. It's going to have a lot of image rejection here for 26.4. Okay, so this is your chain and this is your variable gain here. So I can just put a tune on this and I can vary this one and I can look at this. So it will not change anything except the gain of the chain. Okay, so the gain is going up, right? So basically if I take this up at around 1.5, the gain has gone down. What? So down? Okay, this is a 30 dB loss, huh? So at around 2, it will be a 0. So it will come up. Okay, look at the right hand side. Don't look at the left hand side. Right hand side, that's the gain. So look at the right hand side. So the gain is going up, right? So it's around what, 62, 63 dB gain. Okay, so I am changing the gain over here. It has nothing to do with the compression over here, right? Because this stage is over here. If you want, you can have a variable gain LNA. Okay, a variable gain LNA will give you a larger dynamic range. Okay, a variable gain LNA will give you a larger dynamic range. But here, I am here. And what this stage is doing is, it is only putting you into the right range of ADC. It's not going to do anything over here. What matters is the gain over here, right? So you can have a variable gain over here instead of over here. Okay, this basically variable gain is to adjust your output in the dynamic range of your ADC. Variable gain over here would mean that you are going to adjust the gain of the LNA, and then you are going to change the sensitivity and TOI and everything, because here the bottleneck is over here, the compression of this mixer, right? So if you want to have a higher dynamic range, you can add a variable gain over here. So for example, okay, I have put the gain stage over here, and then only a single gain stage over here. So because any gain variation over here is for ADC adjustments. Any gain over here will be basically your SFDR. So this block, I could have migrated this side. But then if I do this, the overall gain goes up, then the mixer has to compress much higher. Okay, so the mixer design, if there is a variable gain LNA here, you should design for a mixer for the worst case compression, right? So that's going to help. So if you want to have a variable SFDR, you should put a variable gain LNA over here, or you should be able to bypass the LNA. Okay, so if you hit it with more power, just bypass the LNA. So you can put a RS switch here. Okay, and in that case, you can get a higher SFDR and a good sensitivity. So that's where this block should be. So I'm putting here 10 dB gain, and here if I put 0.5, then this will be 22.5. So 10 plus 22.5 will be 32.5 is the gain over here, right? So that is going to affect input TOI, because the mixer is the one which compresses faster than any other gain stage. Okay, so you should know all this kind of stuff. Now you can do all kinds of equations, which is the same equations. You can look at TOI and every stuff. But the idea is I want to do the sensitivity analysis. So here I want to look at the noise figure, signal to noise ratio. I want to look at compression, right? And I want to find out what is SFDR for this thing. So let's go ahead. So don't pay so much attention to this slide. There may be something's wrong over here in equations. I think there are something wrong over here. You can basically just depend on their computation. Okay, don't do this computation. You can do SFDR here. Okay, so let's do that. Let's do a budget analysis of this. Okay, so I'm not going to change anything in the chain. I'm going to keep it as is. Okay, only thing is that this will go Control X, Control V, and this is going to become this, and this is going to short out, and then this is going to go. So if V is 1, then the gain was 15. So I will put here a gain of 15. Okay, so this will be a gain of 15. Okay, and then I will put here right kind of this. So if this is a 20, so 46, this will be 26. And this is 55, then this will be 45, 35. Okay. Okay, makes sense. Before I do that, let's just simulate this once again to see that the compressions are okay. Okay, so let's simulate this once again to see if everything is okay. Okay, gain of 55 or not 54, that's okay. And it is compressing around here. Minus 20, it should compress 1 dB. Okay, so right now, minus gain is 54. So gain of 53. So that's a gain of 53. And so at minus 21.8, it is compressing by 1 dB. So that's all we need to know. Minus 21.8. Okay. It's compressing by 1 dB. Okay. So now I'll get rid of this guy. And short it out. And then instead of this, I will just disable this equation, and I will go to budget. Simulation budget. Okay, here I will do the same stuff. And I will put measurements. Okay, so what do I need to see? What am I seeing over here? I want to look at component noise figure. Okay, component noise figure. Is it recording? Yeah, it is recording. Okay, component noise figure. So that is component noise figure. What else do I want? I want to look at output SNR over resolution bandwidth and NF reflection. Okay, output P1 dB and this. Okay, so let's just put it ourselves. Okay, so what else we are interested in? Component 1 dB? No. Noise figure from system input to component output. Okay, so this is like a cascaded noise figure. Okay, then output P1 dBm. Let's look at the gain compression also. Gain change. Gain change. We can also look at SFDR total. Spurious free dynamic range from third order intercept power level to total noise power at component output. And then there is one other SFDR. It says spurious field dynamic range from third order intercept level to noise power per resolution bandwidth at component output. So this is for a resolution bandwidth, and this is for the total. Okay, so I would put a total here. Okay, what else is there? TOI, SOI, I need not put. I'm okay. Okay, so I'm going to do this budget analysis on this and see how bad the things are. But before that, I'm going to put a power of minus. So not at this. I will put a very low power. Let's say I'm going to put a power of 100, minus 100. How's that? Okay, so now I'm going to run this. Okay, noise again, the okay, the termination is basically, it's objecting to this termination. So, okay, so I'm saying that this resistor doesn't have a thermal noise of it. It is at absolute zero. Okay, so component noise figure. And noise figure reflected. Okay, so this is 8. I understood that. Let's see what is happening over here. Noise figure of 8. Okay, this one, nice figure of 8. Okay, this is just a nothing over here. Okay, then this one has a nice figure of 4. Okay, and this LNA has a nice figure of 3. Okay, so now if you see the definition of noise figure is noise figure of a system from input to the component output. Okay, and this one, component noise figure. So why there is a number of 17 here? LPF is 17. Doesn't make sense though. Okay, this is from the input to the component output. So basically, okay, let's look at the reference. Output SNR, resolution bandwidth. There's this 17 coming from somewhere, and then this is there. So this is not making sense. Let's see what has happened here. Minus 100 in. LPF minus, LPF is 17. Why this be 17? LPF1 is 17. Hang on. LPF should not do 17. It should just do an insertion loss, isn't it? should just do insertion loss. It should not do 17. You should not do 17 here. You should just do the insertion loss of LPF. Just 1 second. Let me put myself to mute. Okay. So I don't trust the model here because this mixer, if I had both sides, it was doing 17 on this, which made no sense. Okay, so now this makes sense now. Okay. Okay, so now these numbers do make sense. Okay, so look at this column. What's important is I have resumed the recording, right? Yeah. Okay, so look at this column. This will be the total noise figure. Okay, this would be always referred to the input of the LNA or input of the or at the antenna at the source. So if I have all of these in the chain, then this is around 6.391. Okay, so basically a detector. Okay, let's do this. Let's look at the signal to noise ratio. Signal to noise ratio, which is not over here. So let's put a signal to noise ratio in the budget analysis. Let's put a signal to noise ratio in the budget analysis. Output SNR, this one, right? Or total, not the resolution bandwidth, total. Okay, simulate. Okay, signal to noise ratio. Okay. Okay, now let's say over here 6.31. Okay, okay, let's read the definition of this one again. This one. Come on, I cannot even change. Noise figure of the system input to the component output. A system input to the component output, right? So this is to the component output, right? So this is component noise figure. Out. Okay. Okay, so this is basically noise figure from system input to component output. And then a signal to noise ratio is ratio of the power delivered to the noise power at the component output. Okay, signal to noise ratio. Okay. Signal to noise ratio. What's the input? Minus 100. Output SNR. This big number. Resolution bandwidth. Total bandwidth. Total bandwidth. let's look at SNR. Resolution, because we are going to look at a channel, right? Okay. Okay. So let's say this is 1/6. Okay. So 1/6 doesn't work here. Okay. So let me explain you what I did. Okay. I'm looking at what signal to noise ratio I would be over here. Like, let's say if I have a signal to noise ratio over here of something like, my detector minimum signal to noise ratio is around 3 dB. Okay. So I'm going to adjust my input power. I'm going to adjust my input power so that I'm going to see 3 dB. So it is stronger. So let's say if I see 3 dB, 3.5 dB roughly. Okay, so that means that the detector signal to noise ratio over here is 3.5, right? Hang on. And at the antenna, I'm at 9.7. Okay, so if this is 3, okay, signal to noise ratio is 3. So let's go down further by 0.5 dB. Okay. So this is 3. And this is total 9, right? So what it means is I would just do this equation. 9.288 is signal to noise ratio in dB, right? So 9.288, okay, minus 3.087, right? So that is going to be the total noise figure of the receiver, which should be the same as over here as 6.391. Okay, so equation, okay, 6 point something, 6.391. Yeah, so what it is saying is if you ensure that signal to noise ratio at the detector is 3 dB, this happens at what power level? It happens at this power level, right? So at this power level, I'm getting a signal to noise ratio of 3 dB at the detector. And at that point, the antenna has a signal to noise ratio of 9.288. And the difference of the two will be the noise figure, which is going to be 6.3 something, right? So that's the whole idea. The overall noise figure of the receiver chain is 6.3, right? And the contribution to each, the contribution you can see from where it comes from, okay? Let's say it's the mixer. The mixer's contribution is around 3 dB here, because the gain over here is 10 dB. So let's say if I was to give a gain of 20 dB, then the mixer's contribution is going to go down because I have already increased the gain over here. Okay, so now the mixer's contribution is 2.9, right? So if I keep increasing the gain, I would see lower and lower contribution of the mixer. While all others, I'm not going to see a lot of contribution because it will be divided by a lot of gain, right? So that's the idea. Okay, so the mixer basically is contributing 3 dB. Okay, so if the mixer has a noise figure, so it's basically the gain of the LNA and the mixer's noise figure. That's you're going to see at the output. Okay, so that's what is happening here, right? Okay, so main important part is how much gain do you put before as a LNA gain? Okay, it's hardly doing much here. Mixer's contribution, nice figure of a LNA. Okay, so nice figure of a LNA and the loss of the BPF. That's going to be there, but then I see a contribution from the mixer of 3 dB on the noise figure, going from here to here. I don't think this guy is doing anything. These guys will not do anything. Yeah, you won't see any effect of these people. Okay, so in this, what I was trying to show you was how do you arrive at a sensitivity number? You say that I want to see a certain signal to noise ratio at the detector. At what level, at what power level will I see that signal to noise ratio, right? So what did I change? I changed here gain. Okay, so I'm seeing signal to noise ratio at 3 dB at the detector, 9 dB at the antenna. The overall noise figure is 6.3 dB. And at this point, the power level was minus 103.5. Okay, so you have to convert this to voltage in a 50 ohm system. Okay, so for that, you can write a simple equation. So it allows me to write equation here. Okay, I would say sensitivity is going to be this power V square by R is, okay, so I have to go to dBm to watts. Okay, so I have to go to dBm to watts, 10 raised to RF power by 10. Yeah, by 10. This is in dBm, right? So I have to do minus 30 on this. So RF power minus 30. Oh, come on. So RF power minus 30 by 10 raised to 10. So this will be in case of watts, and this will be V square by R. So I will multiply this by 50, and I will do a square root of the entire thing. SQRT of entire thing. Okay, so this would be the sensitivity. Okay, so if I put it over here as a table, and sensitivity. So 1.46 microvolts. Okay, so 1.49 microvolts, sorry. So this is going to be your sensitivity. Okay, and the SFDR 102. 102.7 is the SFDR for the receiver. Okay, so you can also compute like this. If this compresses at minus 21, right? So basically you should go 10 above that, right? So minus 10. Okay, 103 minus 10, 103 minus 10 will be in the same range. Basically you can compute that also. Okay, so SFDR from TOI to input TOI to your sensitivity, that is going to be your SFDR. So your SFDR numbers are around 102 dB, and then your noise figure is over here for this receiver is 6.39. That's your noise figure, and your sensitivity is 1.49 microvolts. And then sensitivity you found out at this detector signal to noise ratio, worst case detector signal to noise ratio over here. So this is how you basically are going to work with your receive chain. That's how you do the budget analysis. Okay, so I guess this makes sense, right? So now, if you have any questions, you can write it over here, right? I'm going to unmute you all. Okay. So we are going to take a break. Okay. So we have a way past 2:30 again. So we are going to take a break here, and we are going to put this to a pause. Okay. So now what I'm going to do is I'm directly going to, there are lots of topics left, but I'll cover them, as we go along. So don't worry about if I skip something which you see in the presentation. Sooner or later it'll be there. So don't worry about that. Okay, so now what I'm going to do is I'm going to skip over. So this, don't worry about this fancy stuff, this modulation and all that. We'll revisit this stuff. So don't worry about that. So what I'm going to do is I'm going to look at this PDK. Okay, so what I was trying to do is upload this PDK to a Google Drive and then share it. I don't know if I can do that, or is there a possibility of sharing a file over here? Is there a possibility? Is there a Dropbox here? There's a Google Drive here. My computer. So let's say desktop, and I have a RAR file. I have a RAR file. So this is going to be called GPDK. RAR file. Open. Is it possible to upload this? Yeah, seems like this is possible to upload. Okay, so please, someone tell me, will they be able to download this?
We have that PDK, so.
Yeah, you have that, but can somebody download this and tell me if they can download this from here? So somebody, if you download this and see if you can download this and you are okay with that. Nidhi, right?
Hello. Yes, sir.
Yeah, Nidhi, can you download this RAR file?
Yeah, I can.
Okay, so you are able to unzip it, right? Okay, now if you have ADS, put it into the user folder, right? Put it into PC, C drive, users, and whatever is the name. For example, in my case, it is Anurag. Somebody, it will be administrator. Can you unzip that file over here? You should be able to unzip it, right? If somebody is able to unzip and see these folders in there, we are all set.
Yes, I can unzip.
Okay, fine. So let's go ahead. Now this is very simple now. Okay, so let's make a new workspace. Let's launch ADS. I'll make a new workspace. So I'll call this as design practice, new workspace. So when you do this, again, you are not going to use any white space characters other than underscore. Okay. Design practice. Next is check this setup layout technology immediately after creating the library. Check this one. Okay. If you don't see this, you go to show details and then you can check this one. Okay. So once you check this one, so if you don't see this, you will be just saying hide advanced or show advanced. Should be checking this, check this checkbox. Then you go to change libraries. And in my case, this is there. So I'm going to delete it from favorites. Okay. So in my case, it looks like yours. Okay. Maybe yours look like empty. Okay. So you go here to add user favorite library. PDK. Wherever you have unzipped that, you reach to that folder, and your folder, double click that and click on this lib.def and say open. So as soon as you do open, it will be listed over here. And if there is a pop-up window says okay, say okay. And then it will be listed here with a check mark. Once you do that, click OK and say create workspace. And in this case, it will say, do you want to use this resolution? Say yes, or say finish, and you are done. So you have an empty workspace with your library. Okay, so now I'm going to first test the Nmos and Pmos devices. So what I'll do is I'll go to new schematic, and I will call this as test Nmos def. Okay, so I'll say create schematic, test Nmos def, and I'm going to put an Nmos over here. Okay, so in this case, the length I'm going to put as 130. Okay, width I'm going to put as 2 microns, and fingers I'm going to put here, let's say 10 fingers. Okay, or if you want, you can see what LNA's size is over here. You can do that. Now, few more things I want to tell you. Okay, in this library, you have got Nmos devices, Pmos devices, capacitors, bipolars, MIM inductors, MIM capacitors, inductors, diodes, varactors, and then you have resistances. And as I told you last time, I have only touched Nmos here and Pmos here. And remaining is, other than this resistors and this MIM cap and inductor, I don't use any of the stuff because I don't believe them. Okay, you can try using them, but you will get some absurd response. So don't worry about it. Next thing is you can see that this is the stack up. Okay, now this stack up is more or less like, just a repetition of something. It's just that this is a fictitious process. So you have a stack up. You can do the layouts. You can also do the thermal simulation on those. Okay, so there are thermal layers with this. You can do all your routing and everything. So if you go here, and if you go under library view, under substrates, you will see that substrate. Okay, so this is that substrate. So whenever you want to do an inductor and simulate it, you can put an inductor and simulate it, right? So at present, we are going to do circuit design, not the layout. So we will not encounter this, okay, unless, at the end, I show you how to do it. So this is your stack up. There are certain DRC rules which are very standard here, right? So these are all your DRC rules. Then there are some antenna rules there. And then how to set the GUI to be interoperable mode. So this you do from the main window. This is not a must. Okay, so don't worry about it. Just leave it as is. Okay, all I want to try to do is plot these characteristics. Okay, this is output characteristics and transfer characteristics. So I'm not even worried about Pmos. I'm just going to do Nmos first. Okay, so I will do a 100.13. Okay, 100 by 130 nano. Okay, so let's go to here. So if I was to do 100, so right now the total width is 20. So if I make this as 5 micron, so that is 50. So if I put 20 fingers, okay, so this is 100. So it is 100 by 0.3 now. And say okay. 100 by 0.3 is okay. Now, if you want to see the layout, you can also see the layout from here. Layout, place component from schematic to layout. I don't know if it has placed or if that is broken. I think that is broken. But anyways, you can go here and go to Nmos and you make it 130 nano. And you have a width of, finger width of 5. And you have fingers, 20 fingers, right? And say okay. So that's your transistor. Okay, there are no, this is not the RF version. So RF version is over here. Yeah, but I rarely use this because I don't like the model which is in there. 130, 5, and 20. Okay, So there's not much difference here. I don't know what they did. They should put a ring around it, ground it, put lots of substrate contacts and things like that. Okay, so in the layout, it'll look like this. There are 20 fingers and they are on certain metal, they are combined, right? So you have the drain on this side and the gate on that side, and the source basically is going to be all across stitched on a metal. Okay, so if you want, you can turn off the metals and you can see that which metal is what. Okay, so you should be able to do your routing and everything. Same thing is about inductors. Okay, so you can pick up an inductor here, and let's say the inner radius is 100. Number of turns is 1.5. Okay, so this will be equal to this much nanohenry, it says. Inductor width, I'm going to put as 10. And spacing, I'm going to put as 10. Okay, and say apply. And over here, I can put that inductor. So that's the inductor. So similarly, you can put everything, you know, high res poly. Okay, so this is a resistor, it's going to be very small. So this is the smallest resistor I have placed there. So that's the resistor. Okay, so you can, then in the doc folder, you will have a description of all these components, right? So in the doc folder, you can use that. Similarly, you can work with NPNs, right? You can put here the emitter periphery and multiplier number of fingers, and you will have the layout. The smallest one is just 1 finger. Okay, so that's there. So I'm not going to do a layout for now, but if you are free to do the layouts. Okay, how do I remove the annotation? Tools. I just don't want this to be annotated. This is when you place the component. Clear annotation. Anyways, I'm going to close it. I'm going to open it back again. Okay. So this is 100 by 0.13. And again, there are no information about whether it's a twin tap process, N-well process, and all that stuff. So don't worry about this. Okay, for now, just do this. So this is how a common source configuration is there. I'm going to look at the DC curves. So all I'm going to do is I'm going to put 2 sources, sources frequency domain, and 2 voltages. So one I'll call as VGS. Okay, I didn't hit apply. That's okay. So this, and this one I'll call this as VGS. And this one I'll call the VDS. And then I'm going to connect VGS as is. And VDS I'm going to connect through a probe. Probe components. Just make sure that the probe arrow is pointing in the direction of the current. So in this case, I'll have to mirror this to point it this way. And I'll call this as ID. ID is the current. Sorry. Come on. Okay, if you have problem placing it, just go to preferences and say snap to pin. This may not be enabled. That's why you have a problem. Okay, snap to pin. Of course. Okay, so snap to pin should be enabled. Otherwise, you have problems snapping it. Okay, so we are all set. We can look at the curves here. Only thing is that to do DC analysis, you first of all, you should also include the include file. So in include file, they have given this option. Okay, they have given fast, fast. These are the process corners: fast, slow, slow, fast, right? And nominal, right? And this is statistical Okay, so there will be like a Gaussian and a standard deviation. So that's that. So don't worry, just put statistical, put the include file there. And I'm going to do the DC analysis. So I'll go to simulation DC. Okay, and I'm going to see here VDS. Okay, from 0 to let's say 2.4 volts and step size of 0.01. That's okay. And say okay. So this is your DC. And then I'm going to sweep VGS. So VGS, I'm going to sweep over here. I'm going to go from 0.4 to let's say 0.9 and steps of 0.1. So there are 6 curves. Okay. One more thing I have to do is I have to say that the inner simulation is in DC1. Okay. So now we are all set for doing the DC sweep. And I'm going to plot ID versus VDS for different VGS, right? So this is VDS. Okay, so let's hit simulate. Undefined VGS, of course. If you use variables, you have to define them. So variable VGS default value is 1, that's fine. And then VDS default value is 1. Let's add, and that's okay. Now you place it over here. Fine. So now hit simulate. And here you have ID, and that's your characteristics, right? So this is your DC output characteristics. Now I can do this transfer characteristics in the same simulation window. What I'll do is I'll go here to simulation settings, change the data set to 1, change the name, apply. I'm going to do a VGS sweep here. I'm going to change the sweep the variables. And here I'm going to do VDS. So I'm going to do it for different VDS, which goes from 2 to 2.4, let's say. Okay, 5 of this. Fine. So I'm going to a different data set. It will say, do you want to change the default data set? Say no. And then here you go to a new data set and plot ID. Okay, so this is your transfer characteristics. Now, a little bit about transfer characteristics. Okay, so if you do a log on this axis, y-axis, okay, so this is subthreshold. This is going to give you subthreshold slope. This is going to give you jiddle and dibble over here if you zoom in. And you can also have all short channel effects here, velocity, saturation, and mobility degradation. So if this is output, you are going to look at velocity saturation. And then you can also get mobility degradation. Okay, you can get mobility degradation from here and velocity saturation from these curves. So if you know modeling, you should be able to extract everything out of this. Okay, and again telling you, this is not GPDK 180. This is Silterra. Okay, this is a Silterra process. Okay, so mind you that this I have changed the model inside. Okay, so that's there. Same thing you can do with a PMOS, but then the polarities will be slightly different. This will be flipping up, like this will be mirroring around x-axis, and the source will be connected to VDD, and then the drain, I'll sweep the voltage. So if you want, I can do that, but it's not worth doing it. Okay, so what did I do? I just looked at the device characteristics. So these are your device characteristics. If you want to see the output impedance and all that stuff, you can put markers here, find out the slope, invert that will be RDS. If you find its intersection with 0, that will be your early voltage. Okay, so all these things, if you handle device, you know all this stuff. Okay, so you have the device. Now what is the next thing I'm going to do? Where do I bias this? Okay, so let's go back. I want to burn. So let's put a double click this and say display labels. So what I will know is this is at a 0.8 bias. So if I was at 1.8 and I had a 0.8 bias, so basically I would be drawing in 15 milliamps of current. So if I do 0.75, so I'll be write 12 milliamps of current from 1.8 volt supply. So let's just do that. Okay. So I am going to just say a new schematic and call this as S parameter, S para LNA STG1. Okay, so I'm doing LNA stage 1. Okay, so over here, I'm going to use the same device. So this device I'm going to use as is. And this also I'm going to copy. And maybe this one also I will copy. And this also, so everything I'll copy. Control C, Control V. Okay, it got disconnected. Why? Okay, so if, for example, you have enabled the grid snap, okay, so go to preferences and you will find that this is there, right? So you just say save a copy of preference and say, okay, so it should snap to this and that. Done. Okay, so now I am going to bias at VGS equal to 0.8 and VDS as 1.8. Correct? And I am going to look at its S parameters. But before I do that, I'm going to make sure that I'm somewhere within the Smith chart. So I'm going to put 2 inductors in here. Okay, so 2 big inductors. So let's say I have a turn of 1.5 and I want the inductance inner radius as 100. So what do I have? 1 point something nanohenry. Width as 10. Okay, spacing is 10. Okay, so this is there. So now if I go to 2 turns, this is 3 nanohenry. If I reduce this to 80, roughly 2.4 nanohenry. So I'm going to put it here, here. Okay. Actually, this is too high. This is decoupling actually. At 27 gigahertz, it will decouple. Okay. Just bear with me a second. Okay.